Okay, so here is an example of a constant acceleration kinematics problem. So if you want, pause the video, okay, and then kind of copy down the diagram if you need to. Other than that, I will show you how to attack part A, B, C, and D. So here we have a car that starts at rest, and there are two different positions given to you in the diagram. The first position is 40 meters, the second position is 80 meters, and the acceleration is a constant, or aka in this case uniform. All right, so let's knock out part A. Okay, part A asks us to find the instantaneous speed, aka the absolute value of your velocity. Velocity is a vector, so anytime it says absolute value, find the VF, but do not include directions in your final statement. Okay, so it wants us to find how fast is it moving by the time it hits this first 40-meter mark. So let's knock it out. We can use this particular kinematics equation only because we don't know what the time given is, but we do know a lot of the information. I know that VI initially, the car starts at rest, so that's going to be 0. I know the acceleration is 2. The displacement is 40 because this part A asks us for the first 40 meters. So I would start from 0 seconds and go to 40 meters, okay, or 0 meters to go to 40 meters. All right. I put the 0 meters per second there just as a placeholder, but as you practice, feel free to cross the VI squared term out if it's 0 in your work. All right. So if we simplify the right side, 2 times 2 is 4, 4 times 40 is 160, and then we have VF squared is equal to 160. But to find VF, we would just square both sides. Therefore, if you do your calculator work, you should get a value of about 12.65. So the car will be moving at a speed of 12.65. And I want to point out that this is your final velocity. It's your instantaneous at that point. It's not your average, okay? So this is a value at this specific location. So at a position of 40 meters, the car is currently moving at a rate of 12.65. So make sure you interpret velocities correctly. All right, there's a different way to do it. Okay, again, depending on how you interpret information and your confidence in kinematics equations, if you wanted to, you could have started with the average acceleration function, which is equal to change in velocity over the change in time. In this case, we're trying to find VF. So do a little algebra, multiply both sides by delta t to get rid of that. And then this is negative VI, add VI to the other side. So your final velocity function is AT plus VI. But here, VI is 0 because the problem starts at rest. And then I know what A is. A is given. I don't know what T is, but that's okay. I can go find T real quick. I can use a kinematics equation that has a T in it. In this case, I've chosen the displacement function. So as you practice, hopefully this stuff comes out. Which one to use. It depends on how comfortable you are and how many of these you've memorized. All right. I'm going to cross VIT out because for this particular part, it starts at times equal to 0. At times equal to 0, the car is at rest. So I'll cross that term out. I know my displacement is 40 because it said so. The acceleration is 2. So the only variable I don't have here is my t squared term. Therefore, let's just crank it out. The 1/2 times 2 will just give you a product of 1. So you don't need to write out the 1. Writing a 1 is redundant. So therefore, 1 times t squared is just t squared. On the left side, I have 40. Okay. In case you're confused why this is s squared, the unit meters will cancel out. And then to get t squared by itself, you need to move this s squared unit to the top. But if all your units are in SI units, you don't really have to write units as you practice on scratch paper. Okay. So therefore, to solve for t, we would just square root both sides. Square root both sides will give you a t of about 6.32 seconds. Okay. Now, once we know that time, though, we can just plug it back in to our statement that kind of stumped us. All right. So it's okay if you run into an unknown. If you run into an unknown, learn to just go find it. So here, I carry my work down again. The acceleration is 2. I substitute in t for what I just calculated, which is 6.32 seconds. And then calculator work will give you a value of 12.64. This is 12.64 versus 12.65. That's because I'm rounding and I'm keeping as 12.65 based on the value I'm using on the screen. So really, 12.65, 12.64 is all the same stuff to me, okay? All right, so that's that. Part B. Part B asks you to find the time it takes to reach the first 40 meter. So if you were paying attention previously, by using the second strategy, we actually had to find the time, to find V. So I would just show you again, just in case you attack this part from scratch. Use the displacement function because it has the time variable in it. And then VI is 0, your delta X is 40, your A is 2, a lot of plug and chuck here, and then T is your unknown because that's what it has to find. And that's the case again, the 1/2 and then 2 multiply out to give you a product of 1. 1 times T squared is just T squared. So if you do all this stuff proper again, square root on both sides just to get T by itself, you should get the same answer as we did in the previous slide. However, what if you didn't know this function, right? What if you don't know the displacement function, or you wrote it wrong, or you're not confident? You can always use the average velocity function, delta x over delta t, and you can also set it equal to v average when a is constant, which is in this case. Again, uniform means constant. So to find the average velocity, which is take vi plus vf divided by 2. But both of these expressions represent average velocity, so I can set them equal to each other, which is what I've done here. So in this case, we're trying to find t, but I notice right away t is in the denominator. Therefore, I need to move it to the denominator. So this is what I've chosen to do. You don't have to do the same step. If I see t is in the denominator, I'm going to flip both of the sides of the equation upside down. So if I flip both sides upside down, this is what I have. But you notice t is still not by itself. By doing so, I just got delta t to be in the numerator, which is the proper algebra move. But then I need to get rid of this delta x. So to get rid of this delta x in the denominator, I would just multiply both sides by delta x. So multiplying both sides by delta x will cancel the x on the left side of the equal sign, and there's the delta x on the right side. I like to use parentheses when I do this just to keep my work clean. Alright, so here we have a lot of information already. The 2 just gets carried down, that's part of the function. VI, I plug in 0, just hopefully if you're doing your practicing, you know where values go. VF here is 12.65 because we calculate that in part A. Okay, and then your displacement here is 40 meters. Again, when you're doing calculated work, you don't have to put like ease or positive, because here you're finding time anyway, which is a scalar. So if you multiply 2 times 40, which is 80, that's in the numerator, and then 0 plus 12.65, which is 12.65 in the denominator. If you simplify that on your calculator, you should get the same value of 6.32 seconds. So the point of this stuff is to show you that there's different strategies in solving for unknown. Practice, and then hopefully don't spend too much time on kinematic stuff. All right. Part C asks us to find the time that it takes to cover the second 40 meters. This one, you want to listen a little closer, okay? This one specifically states the second 40 meters, which tells you from 40 to 80 meters. Okay. Here I have an arrow drawn in red for you. So you need to use the information that starts at 40 meters and then ends at 80 meters because it is the second 40 meters. So to find the time, again, I can just employ my displacement function. But here I do want to point out delta x is 40 meters because from 40 to 80 meters, the difference is 40 meters. My VI, however, is not 0. Okay, VI is not 0 because you are no longer starting the problem from xi is equal to 0. You're starting the problem where x is equal to 40. So you must use information at 40 meters. That is now your initial position, and then 80 meters would now be your final. So don't plug in 0. This is a rookie mistake that kids often do. You let diagrams kind of fool you. So make sure you understand where to start, where to stop. This problem starts at 40 meters and it ends at 80, so you must use information there. So I know my initial velocity is 12.65 because I calculated that in part A. I carry the t down, and then the a is carried down as 2, and then t squared I don't know because that's what I'm asked to find. So if you simplify all this, here I just cleaned up a little bit. I left all the units out. So here the 40 just gets carried down. 12.65 t is just 12.65 t. And then again, the 1/2 times 2 is just 1. 1 times t squared is just t squared. The reason I did this is because I hope that you recognize as you practice that this is a quadratic function. Okay, how do I know that? You have a t squared, you have a t, and you have some coefficient. So for me to solve this t, I must use quadratic formula. But for me to use the quadratic formula, I have to set the whole function equal to 0. So for me to set this whole function equal to 0, I must move this positive 40 to this side of the equal sign, to the other side, which makes it now a negative value. And this negative value is important, okay? Don't just look at numbers, you have to look at the sign in front of it as well. Here I've rearranged it so that it looks like a quadratic function. We just write the highest power first, and then the next one which is t, and then the next one which has no t. So it just has that format of a quadratic function, a x squared plus bx, plus c. Okay, so from here, by looking at this function, I know what my a is. My a is 1. The coefficient for the number in front of the t squared, there's no number there, but if there's no number there, it's a 1. Okay, and then my coefficient b is 12.65 because this is my second term. Again, once you rearrange it from highest to lowest power, this is your b. Your b is 12.65, and your c is a negative 40. Not just 40, it has to be a negative 40 because you have to look at the sign in front of the value as well. Because if you don't get your c right, it will affect your quadratic function. Okay, so here I have my a, my b, and my c. I hope you have quadratic solver on your calculator. If not, you can download it or write your own program. Okay, but here I'm just going to use the internet. Okay. So here I have a quadratic solver all ready to go on the internet. Here my a was 1, my b was 12.65, and then my c is a negative 40. Make sure I punch this in right. And if I hit calculate it, okay, quadratic will give you two answers. In this case, I will pick the first answer because I'm solving for time, and time is a scalar. It can't be negative. So here, my first value is going to be 2.619, but I'll just round that to 2.62. So that's how you would find the value using the strategy that I have on the screen right now. Okay. All right, so let me run through this real quick. There's my answer. Okay, so 2.62. However, if you don't know quadratic and that just seems scary really quick for you, then avoid it. But I encourage you not to avoid it because it really is helpful as you proceed in the course. All right, so here is t. I also know the function for t is equal to change in velocity over a. Here, I know a few information. I know my initial velocity, again, as stated, is 12.65 because we found that in part A. My acceleration is 2. The only thing I don't know is my final velocity at 80. Okay, I don't know my velocity at 80, but that's okay. You can go find it. To find your velocity at 80, you can actually start from 0 and go all the way to 80 using this kinematics equation. This is time independent. So therefore, if you start from at the very beginning, where xi is equal to 0, the initial velocity is 0. So again, I want to find the velocity all the way to 80 meters by starting from the very beginning. And if I do that, I can cross out my VI because my VI, based on my decision just then, to start at the very beginning is 0. So I just left that term out. My 2 is part of the function there. Acceleration is 2. But here you notice for delta x, I plug in 80. Why 80? Because again, I'm going all the way back to 0 and I'm going all the way to 80. By doing this, it tells me how fast the car is moving at 80 meters. Well, I just found my VF. Okay, so in this strategy here, I started from 40 to 80, but I don't know what my final velocity is 80. So I can go all the way back from 0 to go to 80 and then find my VF. Once I find that, I can just substitute it in for VF. Okay, so therefore, time is equal to 17.89 minus 12.65 divided by 2. And if you simplify that, you will also get 2.62. I prefer the left side. I like quadratic. I don't mind it. Quadratic solvers are super fast. So hopefully you spend a little time practicing quadratic because it will be helpful and it will save you time on assessments. All right. Here's another way to do it. Again, still in part C. It asks us to find the time during the second 40 meters from 40 to 80. Okay. One, you can find the time that it takes to go the first 40, which I think is easy to do. And then you can also find the time that it takes to go from 0 to 80. So find the time from 0 to 40, find the time from 0 to 80, and just take the difference. So I'll do this twice. I'll set up my displacement function again. But you know that for both my red arrows here, it starts at the very beginning of the problem, where t is equal to 0, and xi is equal to 0, and v is equal to 0. So therefore, in this case, I cross out my VIT because I'm starting at the very beginning, which implies that the object is initially at rest. I want to go to 40 first. So I know my delta x is 40. I know my a is 2. So if I do this again, we find that our time was 6.32. Okay. If you need to, watch your steps a little slower. But then I can also use the same displacement function, But instead of going from 0 to 40, I can find out how much time it would take to accelerate all the way up to 80 meters. So delta x on this side would be 80. Vi would still be 0 because, again, both of my red arrows starts at 0. My acceleration is 2. So cancel that out. So t squared is equal to 80. And then to find t, we would square root both sides. And then here t is equal to 8.94. Now, you hopefully are keeping up. Well, you just found the time from 0 to 40, and then you found the time from 0 to 80. But the question asks you find the time from 40 to 80. So you would just take these two answers and simply subtract, and that'll give you the time, from 40 to 80, which, as you can see, is also the same 2.62 seconds. So which strategy you use, it all depends on how you're thinking about this stuff critically, okay? All right, let's knock out part D. Part D asks us to find the change in velocity between 40 to 80 meters. Again, from 40 to 80, okay? So make sure you understand where you're starting and where you're ending. That's usually where kids make mistakes. They get sloppy and they don't know where they start and they don't know where the problem stops. All right, so to find change in velocity, I can simply write delta V is final velocity minus initial velocity. And then from here, I know my work from the previous slides, in case you didn't keep track. I found the speed at 80, which is 17.89. And then I found the speed at 40, which is 12.65. So therefore, I know my values. My final velocity at 80 meters, again, this work here is for 80 meters, is 17.89. I plug that in. And then the car is moving at 12.65 at 40, which is, again, indicated here in the displacement function that I use. And then if you do that, you will get a change of 5.24, okay? So the car sped up from 12.65 to a speed of 17.89. Therefore, the difference, or the change in velocity in this case, would be 5.24 meters per second. And it is moving in the positive direction, so the change here is positive. So the proper way to express the answer would be 5.24 meters per second, positive direction, or comma east or right. All right. And then the other way to do it is just using your average acceleration equation. How do I know the bus is out? Because average acceleration is delta V over delta T. So you notice here I kept the change in velocity condensed. I didn't break it up into VF minus VI. So to get delta V by itself, I would just multiply both sides by T. That's what I have here in the second line. And then from here, I know that my A is 2. And then I found the change in time from the previous slide, which is 2.62. So it only took 2.62 seconds for the car to go from 40 meters to 80 meters. Therefore, you just plug values in, and I noticed there I did that step twice, so ignore that. But you should get the same value. 2 times 2.62 seconds will give you a change in V of 5.24. Okay. And I want to point out that you need to put like east, or rightward. But then I also want to point out that this is change in V. This is not your final velocity. This is not your average velocity. This is not your initial velocity. This is the change. How much has your velocity changed by during that time interval, or during that distance from 40 to 80? Okay. All right. I hope that helps. Stay nerdy. Don't be whack. Again, you can just ignore this line that I'm going through.